Welcome to the survey of the elementary principles in classical mechanics. Today we will continue discussing exercises and we will begin with a study of a conservative system. The statement of the problem is as follows. A particle of mass m moves in one dimension such that it has the Lagrangian given here, where v is some differentiable function of x. Find the equation of motion for x as a function of t and describe the physical nature of the system on the basis of this equation. So it's a straightforward job to find the partial derivatives of L with respect to x and the derivative with respect to time of x. The two expressions are here. Then I need to take the total time derivative of this quantity and I will obtain the result here. And if you put the two together in the Lagrange equation, you should be able to factor it out in as the following product, where the first factor is just the total energy of the system, and the second factor is Newton's second law of motion, written for a force that is derived from a scalar potential. So what we are effectively describing with that complicated Lagrangian is a one-dimensional conservative system obeying Newton's second law with a force derived from a scalar potential. And the standard form of its Lagrangian is the one given here. The second problem involves a system of two mass points bound by a thread. The statement is as follows. Two mass points of mass m1 and m2 are connected by a string passing through a hole in a smooth table. This thing isn't here, so that m1 rests on the table surface and m2 hangs suspended. Assuming m2 moves only in a vertical line, what are the generalized coordinates for the system? Write the Lagrange equations for the system and, if possible, discuss the physical significance any of them might have. Reduce the problem to a single second-order differential equation and obtain a first integral of the equation. What is its physical significance? Our generalized coordinates will be the radius and angle, giving the position of the mass m1, and we can write its x and y components in spherical polar coordinates. We can take the derivatives with respect to time to find the components of the velocity, and then we immediately find v squared to be given by the expression here. As such, the kinetic energy will have a radial term which includes both masses because they have the same radial velocity. The velocity of this mass on the radial coordinate will be the same as the velocity with which this particle drops along the thread. And we also have an angular component, or rotational kinetic energy, which is just for the rotation of the mass m1. And the potential energy is written as here. It's written in such a way that when r equals L, it will have its maximal value, and when r equals 0, so when I have reached the hole, it will have the minimal value. And from these two expressions, I can immediately calculate the Lagrangian as given here. And I can start deriving the equations of motion for the r and phi coordinates. For r, the equation is given in the box labeled with 1, and for phi, the equation is the boxed result labeled with 2. And we can see immediately that what this equation is saying is that the quantity here is conserved in time, and this is just the angular momentum of the system, which has some fixed value j, and we can use this fixed value in order to solve this equation for the angular velocity and find the expression here. And if we then use this in equation 1, we obtain the following result for the radial acceleration. So notice that if the angular momentum is too small to counteract the gravitational acceleration, then the particle 2 slides down the thread and particle 1 will follow it. But if I have enough angular momentum to cancel out the gravitational acceleration, then the system is in equilibrium, rotating with angular momentum j. But it would appear that I can also have the situation where if I have enough angular momentum to make this term positive, then I can in effect fish M2 out of the hole using the fact that M1 will continue to rotate outward. And of course, in doing all of this, we are assuming that the table is smooth, so no energy is lost due to friction and dissipative effects, as those would ultimately slow M1 down and cause the system to fall under gravity. And the last problem for today involves the double pendulum. We are to obtain the Lagrangian and equations of motion for the double pendulum, where the lengths of the pendula are L1 and L2, with the corresponding masses M1 and M2, and their angles with the vertical are theta 1 and theta 2. This is very simple and straightforward. Our generalized coordinates are the two angles here, and we can write the coordinates of the first mass point accordingly. We can calculate the squared velocity and find the kinetic and potential energy. Here the potential is written in such a way that when the pendulum is horizontal, it should have its maximal value, which is 0, and when it's vertical and hanging down, it should have its minimal value. And then we do the same for x2 and y2, and we can calculate the corresponding values for the kinetic and potential energy. So I was just thinking, yeah, we don't here the angle is not measured as normally in spherical coordinates. So you are assuming that 0 is this way, and this is just 90 degrees on the horizontal, and then it makes sense. So you will have 0 here, and the cosine will be 1 in this direction, so you end up with a minimum value here. All right. So with these two terms, for the energy of the second particle, we can write the whole Lagrangian as given here. And now we can just calculate the equations of motion for each coordinate. So for theta 1, the result should be the one here, assuming everything was done correctly. And for theta 2, the result should be the one here. And that should be all. So thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.